Okay, radians. What are radians? What's the purpose of radians? So, radians are just another measure of an angle. Instead of degrees, you can use radians to describe the measure of an angle. Now, up to this point, you're most familiar with, most comfortable with degrees, but as you progress in school, once you get into calculus, other mathematics, further along in engineering, etc., you're going to be using radians for angle measure much more frequently. And the reason for this is that radians are a much better unit to use for angle measure when it comes to formulas, derivations, just like general physics, science, and engineering principles work much better with radians as the unit for angle measure than degrees. So why is this the case, and what exactly is a radian? And also, once you get further along in school, do you ever use degrees again? The term degrees? Well, okay, first of all, degrees. Where does degrees come from? Okay, well, degrees was invented by the Babylonians, I believe. Don't quote me on that, but, it was invented in some ancient civilization. And the premise is that one full rotation is 360 degrees. And so you could break down a full rotation into 360 pieces to see what a degree means, a degree of rotation. All right, so why 360? Well, there's two main reasons. One is that 360 has a lot of factors, which means it divides up well into pieces, which is ideal, right? So if you think about the factors of 360 starting at 1, well, everything's a factor of 1, but it divides into 2, 3, 4, 5, 6, not 7, but 8, 9, 10, and so on. But that's pretty impressive. The first 10 digits, it divides into 9 of them. Okay, another reason is the fact that, so for the Earth to rotate around the sun, it takes close to 360 days. But days is not something that we made up. Like a day is a full, so like, they could count the number of times the sun rose and fell before, I think it was like before they realized that the night sky finally returned back to like its original point. That's how they could tell that they were, that they had done a full like cyclical rotation about the sun based on the night sky. The night sky would slowly change over the days because the night sky is, if the Earth is here, well, nighttime is you're looking out here. If the Earth is here, nighttime you're looking out here. So they could tell that it took about 300 and close to 360 of the sun rising and falling, 365 about, before the night sky returned to its the same pattern, which was a full rotation about the sun. And that's not, like every planet, that's not the case, that it's like 360 days in a full orbit. Okay? So that actually has a physical principle to it. The fact that, you're choosing an angle measure that corresponds to something to do with the Earth rotating about the sun. That's not completely arbitrary, but still, it's not exactly 360. It's like 365. And it's not like this is a constant parameter for all planets in the entire universe, that it's 365 days in a year, close to 360 days in a year. So degrees are arbitrary. In general, it's arbitrary. It's not based on a kind of natural principle. Okay, and so that's the purpose of radians. Radians, we're going to see, radians are more intimately tied to mathematics, to kind of the physics reality, the physical reality of science and engineering, etc. Okay, but why is that so important? Why is it so desirable to not have definitions and formulas, etc., in science and math be arbitrary? Well, I think your intuition would tell you that if you eliminate anything that's arbitrary, then all of like the math and science ends up being a lot more organized, a lot cleaner. you're able to identify patterns more easily. So it's not like we couldn't just stick with degrees and not use radians, but what you would find is that it would make calculations a lot more cumbersome. There would be these annoying factors going around everywhere. So you're going to see in calculus that, so when the derivative, if you're using radians, the derivative of sine theta, for example, is just cosine theta. That's it. If you're using radians. If you're not using radians, if you're using degrees, it's not like you can't do it. But what you get is this. So if theta is in degrees, right? So you get this factor here. And if you think about over all of mathematics and science and physics, this can just get cumbersome, but then also it's even more than this. Like certain equations might not simplify unless you're using something like radians. So it can be even more than just these additional factors all over the place. To give another example, we know that pi, the number pi, is defined based on it's intimately related to mathematics principles. So if you take any circle with diameter d, so any circle with random diameter d, and you divide the length of its circumference by its diameter, that gives pi. Well, some people have argued that what we should do is ignore pi and instead think about the circumference of a circle divided by its radius. That would be another constant that they would call tau, and instead use tau for the same purposes as pi. And the reason is because they feel that this would result in kind of all of science and math being even more organized, even more cleaner, formulas simplifying even more. So it would reveal more patterns and there would be more insights. And so that's the idea. You go from degrees to radians because you want more of an intimate tie of this quantity of measure to the fabric of math, science, and engineering. You don't want that quantity of measure to be arbitrary, but then you can also think about whatever this new angle measure was chosen to be, you want to choose it as smart as possible. Okay, so with that, what did scientists come up with for this new angle measure for radians? Okay, well, I first want to remind you that when you think about the official definition of an angle officially has nothing to do with a circle. So in one of the opening videos of this trigonometry course, we officially defined an angle, and you really more officially define it in geometry. When an angle is defined, there's no mention of a circle. What's required to make an angle is a vertex and then two straight lines, two straight sides that both have endpoints at that vertex. And then an angle is just the amount of the span or opening between those two straight sides, which you think about as the amount that you have to rotate around the vertex to go from one of the sides to the other side. That's an angle. And so again, you don't have to ever mention a circle to talk about an angle. However, if we're trying to come up with a definition for the measure of an angle that's as intimately tied to mathematics and physics, etc., as possible, then we could consider using a circle, because while you might not need a circle to officially define an angle, there still is a close tie between the two. Okay, so now I'm going to draw a circle in a second like this and explain the tie. But first, I want to remind you that, so here we're looking at a circle in a plane here, the plane of your computer screen. But you can think about a circle or even an angle as being present in any plane, oriented in any way in 3D space. So here's X, Y, Z. So that's another property of an angle. So any angle, all you need is a vertex and two sides. Well, if you have any rays like this, oriented in any way, these define a plane. These form a plane. Like you could take any, let's say this is the computer screen, the YZ plane, but you can take any plane. You could have a plane, like this, and you've got these two, and there's an angle. An angle is like in a plane, and a circle is in a plane. So just note that. Again, that's part of the definition of an angle. It's an angle is contained within a plane. And same with a circle. So how is a circle related to an angle? Well, what you can think about is, so let's say this circle has a radius r, any radius r. Well, if we make an angle in relation to this radius line here, okay, so we've got an angle here, it's the same radius, then there's a relation between the angle and the this arc length, right? Now, I want to pause for a second and just stress that this angle is not dependent on this arc length at all. And the reason is because, again, an angle, you can define an angle without ever mentioning a circle. So what I mean by that is we could have just as easily said, drawn an ellipse, right? And then said, okay, we've moved, so let's just say this is one distance and this is another distance. These two distances don't have to be the same. Maybe they are, I don't know. We've moved a certain angle, theta, and that means we've traveled a certain distance along the ellipse. We could have said that. Like, again, I'm saying like it doesn't matter that these radiuses are the same or if these side lengths were the same. We could have said that. So forget about an ellipse or a circle. Let's just define some like kind of arc that's not elliptical or circular that does like that. Whatever that is, that's a certain theta. And okay, so we traced out a certain arc length there. We could have made this, define this to be whatever we want. However, I think you would agree that the simplest, cleanest way to do this, if we're trying to come up with a kind of natural measure, the most natural measure for angle, would be to just go ahead and use a circle. Circles are arguably the most fundamental shape in all of nature. They provide a really clean representation of what an angle is when you consider the two sides are of equal length. So let's use a circle to come up with this new unit of measurement for angle to replace degrees. Okay, so how can we use the relation between a circle and an angle to do this? Okay, so just really pause and think about what we're doing here. A measure for angle. So the amount of like this rotation about a point here, a vertex here, the amount of rotation. Degrees currently states that a full rotation is 360 degrees. And so like a 360th of a rotation is a degree. So how can we use this a circle here and how the circle relates to the angle to come up with a new unit for angle measurement? Okay, well, first of all, note again that this circle here just has an arbitrary radius r. This isn't a circle with specific size, it's any circle. But what we can try and think about is how much does any given angle represent how far we've rotated around a circle, right? Maybe we can come up with a unit of measure for angle that is based on how far you've rotated around a circle. Now, the issue with that is, well, then, okay, which circle are you talking about? Because we know from life experience that, you could be looking out at something at your house, and you could pivot your head left to right plus or minus 15 degrees, so 30 degrees, and you're looking at like the total front of your house doing that. Or you could be in the mountains and looking, you're looking 5 miles at a mountain range, and you pivot your head plus or minus 15 degrees, 30 degrees, and you're looking over like miles of span, right? The angle has no dependence at all on the size of the circle. Well, okay, that's not a big deal, because what we can do is we can normalize based on the size of the circle. So it's kind of like density. Like the density of steel, for example, you take the mass of a piece of steel and divide it by its volume, and now you've kind of factored out the size from that parameter. All steel, big or small, any piece of steel is going to have the same density. So that's what we want to do here. We want to normalize based on the size of the circle. So what does that mean? How do we do that? Well, okay, let's come back. Let's say we're thinking about how far have we rotated around the circle, but we're thinking about a circle, big or small, whatever. Well, okay, how much you've rotated about a circle? Well, we know what that kind of how that works. If you go a full rotation about a circle, then that's 2 pi r. Right? If you go all the way around a circle, that's 2 pi r. And so what we're trying to find some relation between this and 360 degrees is what we're trying to do. But okay, like with density, you're trying to kind of take the size out of a parameter for mass or weight, and to do that, what you do is divide by size. Well, here, let's go ahead and divide by r. Okay, so this, you get 2 pi. Now, what was this? This corresponded to 360 degrees, a full rotation. That's what 2 pi r was. So now we just normalized by r. So now this didn't work. This relation didn't work. 2 pi r to 360 degrees didn't work because the size was part of the equation. And we know that angle isn't dependent on size. But now we've normalized with respect to r. Now this should work. This didn't work, but this should work great, because it doesn't matter what the size of the circle is. The radius doesn't matter. Okay, now, so you're probably following along with this video fine so far, but then at this point, you might be thinking, well, okay, I get it, but what do we do next? Well, remember, so with degrees, the idea was the Babylonians or whoever, they stated that a full rotation was 360 degrees. And so, you could, a 360th of a rotation is 1 degree, and so that was it. Once you state that this is a full rotation, then that's it. You define your unit of measurement for angle. Well, we're going to do that same thing here with this number. We've got this number here that represents the amount of rotation around an entire circle, but that number is not dependent on the size of the circle, which was important. And so we're gonna say, well, okay, 1 full rotation around a circle is equal to this number, and that's it. You could divide this up into however you want, right? So a half rotation, 180 degrees, would be just pi. 90 degrees would be pi over 2. Now you might be saying, well, okay, but what? So this is degrees, or it's radians, right? What is this? Well, if you take a look at how this was derived, this number is unitless. So we started with 2 pi r. Pi is unitless because it's circumference, a distance, divided by diameter, which is a distance. Distance divided by distance, that's unitless. Okay, but then we had radius, so 2 pi r is a distance, but then you divide by radius, it's unitless. So this number is unitless. In fact, that's one of the reasons why it works well as a unit of measure, like in physics and in math, etc., in place of degrees. It's unitless. It's just a number. You never have to do any conversions, things like that. There's a lot of analysis that you'll see is done in engineering, science, etc. It's called dimensional analysis. It's where you make all of the units dimensionless and kind of analyze formulas that way. It can be really valuable. Okay, so this is dimensionless, but you'll see, though, people might specify that they'll put radians just to indicate that it's radians, or just RAD. Okay, now you might be wondering, well, man, what is this? Pi is like 3.14. This is so non-intuitive, it seems. 90 degrees is pi over 2, and, it just seems like a hassle. Well, you're right. That's what everything I just said is true. And that's why we don't just eliminate degrees. Degrees are still used. What are degrees used for? Well, if you're ever just talking about like the angles of a triangle or the angles of a polygon, or, you know, like if you're building something, you're working in construction, you're talking about angles, or, you know, if you're in the mountains and you're describing the angle, you're going to use degrees. You're not going to tell your friend that those two mountain peaks are separated by, you know, around pi over 4 radians. You're going to say degrees because it's just easier to visualize. It 360 breaks. It has a lot of factors. You can think about what is 15 degrees, 30 degrees, 45 degrees, 60 degrees. It works. It's great for that. Radians is not useful in that context. I mean, 1 radian is about 57.3 degrees. I guess you could try and think about it that way, but not really. It's going to be a hassle trying to use radians that way from an intuitive, like visual, just general geometrical perspective. But however, outside of that, from a physics formulation standpoint, math standpoint, all of the formulas, the derivations, the kind of connection between the different pieces in math and science and engineering, etc., radians is going to be immensely better suited for that purpose. Okay, now the last thing I want to talk about is you still might be scratching your head a little bit. You probably understand how we have this new dimensionless unit here. So like 2 pi corresponds to a full rotation, and the same way that 360 corresponds to a full rotation. But you still might be a little confused like, how is this related to the circle? You know, we just derived it, but if you're like me, after just looking at the derivation once, I was still a little bit confused. Okay, so what this number represents is the amount of rotation from an angle perspective that you need to go all the way around a circle. I'm going to say that again. This number, this unitless number, represents the amount of rotation from an angle perspective that results in going all the way around a circle. And you think, okay, go all the way around a circle. What does that mean? So I guess the circumference of a circle. It's the only way I can think about going around a circle. Okay, so then you ask, well, all right, well then what circle? Well, it's any circle. The amount of rotation from an angle perspective that's needed to go all the way around any circle, no matter what the size, any circle. Okay, to illustrate this, let's think about what does 1 radian mean? Right? What is 1 radian? Not 1 pi. You know, this is 3.14 times 2, 6 point something. No, okay, what is 1 radian? What does that mean? Well, all right, if this angle here, let's say this angle was 1 radian. Well, what you can see is that you can draw however many circles you want that have different sizes, different radiuses, but 1 radian is always just 1 radian, even if you're changing circle size. The difference, though, is that the arc length that's needed to trace out, like the span of 1 radian, gets bigger as the radius increases. That's the difference. Okay, and so what's happening is that 1 radian, an angle of 1 radian, corresponds to moving an arc length. The length of the arc is equal to the length of the radius on any one of these circles. Again, the length of the arc for any one of these circles that go across 1 radian, that arc length is equal to the corresponding circle radius. Okay, the name radian comes from, it's obviously derived from the term from radius. And so the idea is you've kind of gone like 1 radius around the circle. That's what a radian is. You've gone a radius around the circle, a radius. And when you've gone all the way around the circle, how many radiuses have you gone? You've gone 2 pi radiuses. Okay, that's the idea. That's how this represents the amount you've rotated around any circle from an angle perspective. And if you're thinking, well, you know, that's pretty cool, but I feel like the science and math community could have come up with something a little bit better than that, you might be right. And if you can come up with something that's more clever than this, that's what people win Nobel Prizes for. Okay, so that's radians.